This is Maggie. Today we're going to be talking about DNA replication, which is the process that takes place in the S phase of the cell cycle for eukaryotes, and it's the process of copying all the DNA in the nucleus. Eukaryotes have many ories or origins of replication on each linear chromosome of DNA, which is where DNA replication takes place. So to begin, let's start by we're going to go ahead and draw a DNA typical double helix DNA strand. This is the tertiary structure of DNA. It's held together by hydrogen bonds. Okay. And these are the ories, okay, or the origins of replication, which is where DNA replication takes place. Okay, and for DNA replication to take place, an enzyme called DNA helicase unzips this double helix structure by breaking these hydrogen bonds, okay? And two enzymes go in at two different directions, creating what they would call two replication forks. The replication forks right here are going to go in after the enzyme unzips. So say that this enzyme is unzipping all of this. So it would now look something like this. Okay, the DNA, and this is the forks. Sorry, I don't know if anybody can see. This is the forks pulling it in an opposite direction, okay? Now the helicase is the enzyme is causing this right here. We'll put the enzyme here to unzip, and it's creating these two replication forks to pull. Okay, now here's the origin. And it's creating what they call the replication bubble, okay? So, to better draw a picture, we'll just turn that over, I guess, or let me see, just turn it over. The DNA would look something like this. And here is the enzyme, the DNA helicase, okay, which unzips this DNA down here. Okay, now in order to keep this DNA open and keep it from hydrogen bonding again, single-stranded DNA binding proteins hold this open to keep those bonds from forming. So we'll just put those up there. We're going to put those up there. Okay, and now these single-strand binding proteins hold this DNA open. Now, when this bubble that's on this side that we had talked about forms, it creates stress or supercoils within the DNA, which can also prevent this from staying open. So in order to prevent that from happening, DNA topoisomerase, which is an enzyme, makes cuts in the DNA. It unravels the coils, reseals, and then reseals the DNA back up. So we'll go ahead and add that in. Okay. Now that it's all open and everything, the next thing is that DNA primase, which is actually RNA polymerase, adds RNA nucleotides through the complementary base pairing to create RNA primer for the DNA polymerase 3 to extend from, because DNA polymers can only add nucleotides to an existing strand of DNA. However, RNA polymerase can make strands from bare DNA. Now, remember that DNA is anti-parallel, and it's always it's paired off of complementary base pairing. So we'll put this in is 3, 5. Okay, so we're going to put the 5 in here, the complementary, and the 3 in here. Now remove it. It always moves from 5 to 3 in. So let's get a different color here. The primer, or the primase, is here, okay? This is going to be the 5N because that's 3, so it's complementary. So DNA polymerase 3 constructs DNA nucleotides into new DNA strands by creating phosphodiester bonds between nucleotides. It adds nucleotides through complementary base pairing to the 3' end of the strands. So it's going to add this way, okay? And this right here, this strand that we just did, is actually called the leading strand because replication moves continuously towards the opening of the fork. So this is the leading strand. The bottom strand's a little bit more difficult. It's called a lagging strand. It takes a little bit longer. So let's label this one as leading. And this one, the lagging, okay? It's created by DNA polymerase 3 enzyme as well. And it moves away from the fork though. See, so we're gonna go from the 5, which would be here. This is the 5, and this is the 3. This is the 3 on this one, sorry. And it's gonna move away from the fork in the 3 or the 5 to 3 direction as well. And replication is done in sections called the Okazaki fragments. This is called discontinuous. The lagging strand is called the discontinuous replication, and the leading is the continuous replication. So in this, there is going to be, because it's based off of that, it takes a little bit and it has to keep reforming. So it needs to recreate the primer. So it has the primer, and then it stops, and then it has the primer, and then it stops, and then it adds primer, and then it stops, and it just continues on that way as to where the primer, and then it's continuous. So it recreates or generates through that. Okay. Next, we have, we want to make sure that we want to remove all the RNA primers. In order to do that, we add DNA polymerase 1, and it replaces the RNA primers with DNA nucleotides, so RNA is no longer left. So we are gonna now add DNA polymerase 1, which removes the primers and replaces them with DNA nucleotides. So RNA is no longer left. Now this leads us into the final phase of DNA replication, or the final stage. It can now ligase, which glues or bonds these fragments together through catalyzing the phosphodiester bonds. So I don't have another color, so we'll just use black. So now we're gonna ligase these together after, we forgot to remove the one up top, the polymerase 1, and then now all these are bonded together. Now we have 2 identical, you can't see, strands of the double helix nucleotides. They are semi-conservative because they have the old strand and the new strand. And same down here, the old strand and the old strand and the new strand, and they are identical.